So we have one more presentation before our break. I'd like to introduce Professor Iain Coburn from Boston University.
Good morning, thank you. I heartily recommend you to read the somewhat lengthy paper that Scott, Jack, and I have written on this. I don't have time this morning to delve into, I think, some important details and subtleties. The paper begins with our motivating example is to think back a half dozen presidents and reflect on some science policy initiatives from the 1970s. And I think there's, President Nixon, in short order, both declared war on cancer and launched Project Independence. And I think when we look forward from that episode, there's two very dramatically different experiences of these two sectors. As the chart shows, breakdown of federal non-defense R&D spending, you can see the blue part there is health, energy is the green part, and there's been really a dramatic difference. And I think tracing out why that might have been and what the implications have turned out to be 30 years later for the technological progress in this sector is very interesting. One thing I think we can say about the life sciences sector is that a capacity has developed in this country and in others, which I think is truly remarkable. Not just the ongoing stream of very important innovations, but also this kind of institutional technological capability to get on and solve problems quite dramatically. This is the nasty green thing there is the HIV virus, and the chart to the right shows what could have been the kind of disaster we see in places like sub-Saharan Africa, taking off in the United States, but really nipped in the bud. And to a great degree, I think we can attribute this to the ability of the life sciences system, both fundamental scientific work supported by taxpayers and the commercial part of this sector, to get on this problem and come up with a pretty dramatic response. Now, HIV/AIDS, of course, is not cured. These treatments are palliative rather than curative, but it's still, I think, a dramatic illustration. Many of the same stories can be told. Tremendous progress in dealing with some very difficult problems in human health, in the areas of mental illness, heart disease, sometimes some types of cancers, and so forth. So, to first order, you think about what's going on in this sector in terms of innovation, and has it worked? Absolutely. Clearly, government support and government policy has played a very important role. And in our paper, we sort of work through and think, what do we understand as being key drivers of this life sciences innovation system? The first and perhaps most obvious, I think, is a very high level and a relatively stable level of public funding for basic research. A lot of money gets spent through the Public Health Service, some of the other agencies, particularly NIH, but also through some other programs. That has contributed to and supports a process where we've developed a very large, very highly skilled and highly specialized R&D workforce. And that has taken place against some interesting aspects of the economics of pharmaceuticals, which are very different from a commodity product like energy. And I think it's obvious but worth dwelling upon. These changes, public support takes place against the background of fundamentally very high willingness to pay for new products, differentiated new products. If you couple that together with insurance-driven demand, the restaurant where he or she who orders doesn't pay, and an interesting role of quite stringent regulation on the health and safety front by FDA about who is allowed to sell products, this has generated demand factors which I think have been very conducive to commercialization building upon these infrastructural investments in basic science and workforce development. Fourthly, we see this is a sector which, in our view, the critical factor is that there's a bottom-up process of project funding and project selection, if you like. Much of the NIH budget and other agencies, money is distributed to work on problems principally through a process of peer review and investigator-initiated projects. The inmates run the asylum here. We also see this as a sector where the patent system seems to be working pretty well. Information communication technologies and software, people are really scratching their heads and I think are very worried about the costs associated with the patent system, which appears to be bogged down a little bit out of control. In this sector, at least so far, intellectual property rights have worked pretty well and play a very important role in allowing innovators to capture value from their work. And to echo something Ashish just said, these intellectual property rights support an active and important market for technology. Lastly, when we point to key drivers here, I think it's the pervasiveness and intensity of competition, not just in the product market, but all the way through the value chain. I'll expand upon some of these ideas in a moment. Thinking about what has happened since the 1970s focuses us on I think, as economists, on the evolution of industry structure. A lot has happened in this business. This is a gross oversimplification, but this is a way of thinking about industry structure what I would call the good old days. This was the set of institutional arrangements prevailing in the 1970s and through into the 1980s, which created the Z drugs, Zantac, Zoloft, Zocor, and so forth. This was one in which there was a relatively distinct boundary between public sector science and commercial science, which was largely conducted by, big pharma is the term people throw around to describe large vertically integrated companies that do everything from bench science through to sales and marketing. As the industry evolved, not least because of sustained support of basic science, things got a lot more complicated. On the one hand, public sector science expanded, and big pharma shrunk somewhat, but we also saw arrival of a lot more different players. The growth of biotech industry, which operates at the interface between public science and commercial science, and the arrival of new competitors, companies like Amgen, or Biogen, or Genentech, which operate in parallel, essentially as large integrated companies, rather than being R&D boutiques or specialists in particular technology. Now, the evolution of this industry structure has had very interesting effects on who the list of players are and how they interact. This radical change in the science, a de-emphasis of chemistry as a technology, and an increasing emphasis on biology reflects the transformation of fundamental science, but it's driven by and has interacted with a variety of interesting economic phenomena. These would include things like the emergence of new entities. We're familiar now with these science-based entrepreneurship companies, the small-scale, close to university, dedicated biotechnology firms. But at the same time, we've also seen the rise and consolidation of academic medical centers and the appearance of a whole lot of infrastructural entities, venture capitalists, patent lawyers, university tech transfer offices, and so forth. All of this sort of ferment in terms of different types of organizations has been accompanied by an adaptation and adjustment of the large incumbent firms, the federal agencies, the universities, and other established players in this sector. The end result, and this is not a picture of a biotechnology product, it's not an engineered antibody, it's a map of the industry drawn up by some colleagues in sociology. The detail is not important. It's just to illustrate, this maps out connections of different kinds, financial, commercial, technological, between different kinds of entities. Innovation today takes place in the context of this very complex, dense, interrelated network of institutions. All of that has to do, I think, with conscious policy choices and some self-organizing evolution of this system. With that as background, let me now turn to what we think are important lessons to draw for thinking about how to promote innovation in climate change and energy technologies. Point number one, and this I think is becoming a constant theme in these presentations already. It takes a lot of time. The investments that began with Nixon in things like the war on cancer and setting up the National Cancer Institute and so forth pay off decades later, and that is truly fundamental to thinking about these problems. The fact that the clock needs to run for a long time, I think, focuses us also on the value of sustained funding, or alternatively, the costs of instability. And one thing which I think has built the capacity to innovate in this sector is things like labor market development. A lot of people have to make long-term, highly specialized commitments in human capital. In an environment where the budget goes up and down, that becomes kind of a courageous choice for an ambitious young person. Instability in funding, therefore, can only lead to underinvestment in specialized human capital or other kinds of investments. When we look at the decades it takes to take on problems like cancers, the level of sustained attention and career development specialization, you really need this to be operating in a stable factor. Secondly, as I pointed out, the inmates run the asylum in the sense that much of the cumulative advance in biological sciences and biomedical sciences is driven by investigator-initiated and peer-reviewed funding allocation. There's not a lot of top-down command and control. Now, there are public health priorities identified which steer funding. There are political considerations, who sits on which committee. Can at the margin move funds around. It's certainly the case, too, that the product market for pharmaceuticals also generates incentives which steer resources. But the basic innovation agenda is driven by the curiosity of individual researchers. And I think it's that role of curiosity, academic freedom, entrepreneurship, outside of top-down command and control institutions, which has generated a diversity of experimentation and long-term benefits in terms of the accumulation of knowledge and the advance of science here. Thirdly, competition. This is a business which is intensely competitive at all levels, and much of the competition is focused on innovation. Being new and being first is really important in almost all of the activities that go on in the life sciences. In the world of universities and taxpayer-supported research, there is intense Darwinian competition amongst individual investigators, between labs and between universities, looking for grant funding and the Nobel Prize. That generates, powerful competitive pressures to move forward, to be first, to be new. Taking a step away from academic research into the world of commercial science, there's a very active interface now between the market and taxpayer-funded research, which is the biotechnology industry. There are thousands of entrepreneurs working just off campus, mostly funded by private equity and venture capital, competing in this market for technology. They're chasing after resources, talent, and opportunities to come up with new ideas, move them forward, and then sell them to downstream collaboration partners. And then finally we get to the product market in pharmaceuticals. Again, I think the noteworthy feature about this is, the prices are high, but it's also intensely competitive. It's a fragmented market driven largely by what we call Schumpeterian competition, that is to say, coming up with new molecules to compete against the existing set of products. That's one important dimension of competition. Another is that the market institution has been set up as a kind of a push. You get your new product, it's patent protected, or FDA protected for some period of time, but then you get savage competition for your products within your molecule from the generics. That creates a powerful incentive to move on, find new things, keep going. To echo something that Ashish was talking about in terms of antitrust policy, I think once you recognize the pervasiveness of competition, its connection, and its role as a driver of innovation here, I think it connects us to thinking about antitrust policy and how valuable competition is at all points in this process. And that one thing which I think is remarkable about the life sciences sector is there isn't really a choke point at any of the levels of this chain. We don't see domination of activity by single entities or individuals. That creates valuable competitive pressure. It also supports the diversity and experimentation. Fourth lesson, transparency and openness. Life sciences, I think, are uniquely close to academic science, and academic norms, Mertonian science, sharing, priority, disclosure, turn out, I think, to pervade a lot of activity, not just in the world of universities, but also in commercial activity. These Mertonian norms support very valuable things which are not obvious at first glance. They support transparency and disclosure, and these drive, I think, the cumulative advance of technology. I think it's worth noting this occurs even in very close to the market commercial activity. Pharmaceutical companies conducting late-stage clinical trials are still doing so largely under the rubric and in an environment which is pervaded by norms of academic science. We see things like pressure to disclose clinical trial results, operate registries. A lot of this stuff is published and observed in real time and not conducted under conditions of commercial trade secrecy. Now, IP and patents play an important role in creating product market incentives. Interestingly enough, they seem to have managed to coexist with open science. 5 or 10 years ago, I, like many other people, was very worried that the propertization of science was going to cause a train wreck, and that the reach of the patent system into basic science and universities was really going to choke things up, cause all kinds of problems with access and sharing and transactions costs. That doesn't seem to have happened. In this industry, people seem to have learned to live, and that open science and exclusion-based intellectual property rights so far seem to be coexisting and supporting disclosure, providing incentives to innovate, and driving this cumulative technological advance. Lesson number 5 is the product market and the role of rewards to innovators. In the health area, there's just an intrinsically high willingness to pay. There's a lot of money on the table. A lot of it can be captured by new products. The institutions of this marketplace, I think, are very important to the extent that they allow an innovator to capture a significant share of the social value associated with their invention. New drugs are really expensive. That means that the innovator is capturing a lot of the social value, at least until follow-on competitor molecules arrive or they lose market exclusivity and the generics start to eat their lunch. Now, that ability to capture value is driven principally by strong and workable intellectual property. Unlike these areas where IP seems to be controversial and difficult, for a very long time, patents have been ordering property rights in this area. There's historically broad consensus on the rules and norms for what can you patent, what are the processes and standards, how do you enforce them, and so forth. This IP system operates in parallel with very stringent regulation about who's allowed to sell drugs. The FDA stands, between commercial operators in the marketplace. We have the Hatch-Waxman Act and similar infrastructure around this, which operates in parallel and creates this combination of push and pull incentives for innovators to keep moving forward. My last lesson here is to pull together some of these thoughts, is to think about the value of diversity, experimentation, and adaptation. I mentioned the plethora of new ways of organizing activity, new entities like biotechnology companies and university technology licensing offices that sprung up. That also needs to be seen in context with this willingness, I think, of the established players who dominated the industry in the 1970s and 1980s. Rather than resist or ignore these changes, they've adapted, accommodated, and developed a fruitful way of coexisting. So life science is commercialized today largely in the context of flexible, cooperative relationships across a wide variety of institutions. And I think it's been the emergence of an industry culture and government, and a light touch from the government in terms of regulating activity, which has allowed these entities to sort out amongst themselves and to organize themselves and to develop the ability to interact, which has been such a powerful force. So to conclude, the life sciences are special. They're uniquely close to science. They're a unique kind of product market. But I think there are some general lessons that we draw from thinking about this sector. One is to focus on the cumulative process of technical change, which builds upon multiple technologies and multiple sources. And cancer wasn't cured by Nixon within the hoped for 3 to 5 years by coming up with a magic bullet. In fact, it takes 3 to 5 decades to make substantive progress. We do think, however, that looking at this sector points us to the value of sustained and stable public investment in early-stage, general-purpose, platform-type technologies, and secondly, to appreciate the value of and to support and encourage diversity, experimentation, and competition. Thank you.